My name is Lasse Sandstone. I'm here to talk about CPU and GPU based rendering, some of the advantages and disadvantages of each type of rendering, with a focus on GPU, mainly because that's the new way to do it, and that's more interesting than doing it the old way. Here's the agenda. I'll try to be brief. I'm not very formal, so if you have any questions, feel free to interrupt me on the way, and we'll do a summary at the end as well. Who we are, I won't do a lot of time on this one, but it's always nice to know who's talking. Nextron is a small Norwegian business. We have been operating since year 2000. We are a Supermicro distributor, and Supermicro is one of the biggest manufacturers of servers, workstations, and storage systems in the world. Number 4 at the moment. It's Nasdaq based, and it's always very rapid deploying new technology. So when Intel launched new CPUs earlier, a month ago approximately, end of March, we had the systems ready to ship the same day, which is always nice to say. And we have a 5-year warranty as a standard, and of course the prices has to be competitive, otherwise nobody will buy from a smaller vendor than HP and Dell. So that's us in very brief. We are also, of course, in business here in Sweden. We have an office here in Stockholm with local technical staff. Andreas is at the back there. We'll be happy to help you if you have any problems with your systems here. Okay, CPU-based rendering. That's the traditional, the classic way to do it. And how does that work? Well, basically, all the tasks are done by the CPU in the system. And a CPU is a versatile processing unit. It can basically compute all tasks you have, no matter what it does, no matter what it is. It can do many operations at a time. It has typically quite high clock frequency. And modern CPUs have several cores. The one that we have here, demo system, has 2 processors with 12 cores each. And each core also has a technology called hyper-threading, which enables it to parallel some of the tasks, which means that if you open the control panel on that system, it will actually report 48 cores, 24 physical, 48 hyper-threaded. Each core in a CPU has dedicated cache, which means that operations are stored in memory as the computer is processing them, and that gives improves its performance, basically. For a software developer, it's very easy to code for a CPU rendering, because CPU is what it's always been. You don't need to change anything. All the compilers support CPU rendering directly. Simeon, you have to correct me if I'm saying anything wrong now, but that's how I understand it anyway. GPU-based rendering, on the other hand, that is an alternate way to go. In a GPU-based render system, each core is very specialized. It's not a general purpose tool that can do anything, but it's very good at doing the same computations over and over again. So it's really good at tasks that are parallel, where you can do, where you have the same type of calculations hundreds, thousands, millions of times. And incidentally, that's very common in render jobs, because you do the same calculations over and over again to see how will the light reflect on this object, etc., etc. It's the same type of calculations. The results aren't always the same, hopefully, otherwise it would be a very boring picture. But the job is the same. Each core in a GPU does not have any cache, So it's not as versatile, it's not as powerful for a single task. But the difference is that in a GPU, you have a lot of cores. And I'll do a comparison in a second about the number of cores in GPUs versus CPUs. From a coding point of view, using a GPU requires adapting the software. Either writing it from the ground up or and using standard libraries to activate the GPU for computing tasks. NVIDIA, which is the... We can do a show of hands actually. How many are using NVIDIA graphic cards in their workstations now? Either GeForce or Quadro or Tesla? Yeah, pretty much. And how many are using AMD, the Radeons and FirePros? Right, so some of it, but quite a lot of, big majority was using NVIDIA's. And you have to code to actually activate the GPU for a compute task. And the code you use to activate the NVIDIA GPU is unfortunately not the same as when you code to activate a Radeon GPU. So there is a, yeah, the software has to be adapted to be able to activate it. I'll just leave it at that at the moment. Okay, here's the comparison. CPU, powerful all-round cores. That's one CPU core. It's blue because Intel is blue. And the biggest CPU for dual processor systems today is has 22 cores. And why do I only look at dual processor systems? Well, that's because the multiprocessor, the 4-ways and the 8-ways, they are very expensive. So comparing price versus what performance you get, dual processor is the most optimal from the CPU point of view. The only time a 4-way or an 8-way is actually cost efficient is if you have a software that has a license, with very costly license, licensed per server. Then a 4-way and 8-way may be a good way to do it. But from a performance point of view, it would always be better to have 2 dual CPUs rather than 1 4-way. So 22 cores, and as I said, that can be hyper-threaded. So to give the CPU all the advantages it can, let's assume that the software supports hyper-threading fully. So you actually get 44 cores out of 1 CPU, and then you have 2 of them, so you end up with a total of 88 cores. That is the highest core count per a single system with 2 CPUs you can have today. That's the E5 2699 version 4, and it was launched in March the 29th. So it will be the top performer for at least 12 to 16 months. That's the typical release cycle from Intel for these kinds of processors. Okay, let's compare it to GPUs. Oops, there we go. A GPU has small specialized core. That's a GPU core. It's green, that's the NVIDIA color. And it's very tiny, but it's not alone. That's 10 cores, but the normal modern GPUs don't have 10 cores. They don't have 100 cores, which you see there. In fact, the most powerful GPU you can have today has 4,992 cores. That's the Tesla K80. And you're free to count if you like. It should be great. So one K80 card has almost 50 times as many cores as you can have with the dual CPUs. However, in a modern system, you don't actually, you can fit more than one card. So we need to make room, because you can have more than one GPU in a 1U form factor. In fact, you can have 4. That's the highest density today. So 2 CPUs, 88 cores, has to compete with almost 20,000 CUDA cores for the computing power. And of course, this is not very advantageous for the CPU. A task which is optimized for GPU compute will be significantly faster executed in a GPU setup than in a pure GPU setup. Sorry, pure CPU. Okay, so what are the performance gains? How much are we really talking about? Well, it's dependent on several factors. Firstly, how easy can the task that you're trying to do be parallelized? Some tasks are very easy to do in parallel, and some aren't. Rendering is good for parallelization, so that's optimal for GPU, but a more general sort of compute task may not be it. So it depends. Also, it depends on how is the software in question adapted to use GPUs. Is it just converted to support it using a library, or is it actually written from the ground up to support GPUs? Not everything is. V-Ray is starting to support GPUs more and more, but it's on an adapted platform. Isn't that correct? Yeah, sort of. They can talk about that later if they want. Also, when you boost the performance with GPUs, will other bottlenecks in the system be limiting the performance? And both the LAN speeds, the networking speeds, and the disk speeds may very quickly become bottlenecks that will slow the system down. And there are ways around it. We'll talk about that later. And of course, which CPUs and GPUs are being used. Some GPUs give more power, while others give less. And sometimes the CPUs and the system can actually limit the amount of tasks they can send to the GPU, so you can't actually utilize a super powerful GPU on a slow CPU. So they have to match. But the rule of thumb are as follows. If you have a software that's only partially optimized for GPUs, you will get 2 to 5 times quicker execution. If you have a software that's written from the ground up for GPUs, it will be approximately 10 times faster. And if it's really perfect for parallelization, the tasks are just in the sweet spot for GPUs, then you can have as much as 100 times performance gain, which is, of course, very significant. And what does this mean in practice? Well, if you have a task that takes 5 hours to complete, a renderer that you put on as you go home from work, and it will be finished when you come to the job in the morning, well, you can do that in the lunch break instead, and do another task as you go home. So it's significantly faster, and for environments that do a lot of rendering, animation, movie production, that kind of thing, they will feel that this is really, really giving them something extra. Okay, which software supports GPU acceleration? Well, there's a full list on the NVIDIA webpage. There are some of the examples from the media and the entertainment category, which I think is most relevant for you. There are many examples from other categories as well: production, large data analysis, medical, etc. But as you see, there are lots and lots of commonly known and commonly used programs that do support GPU acceleration to a larger or smaller extent. It varies from company to company how far along they are. But I think I can say quite confidently that all of them are getting better and better at supporting GPUs, because this is very, very much in the moment. It's something that all of them wants to be better at. Okay, I'm going to give you some examples of systems that are optimized for GPU use. And the first is common rack servers. The one at the top there, that's the 1U. We call them pizza boxes. And that's the one I talked about that has room for 4 GPUs. You see here that it has 3 in the front, 1, 2, 3, and then there is 1 in the back there. It has to be upside down to get the connectors at the right side, but it's a forced card there. The big one, the 4U one, that has 8 GPUs at the back. And an interesting point of this one is that it actually has all the GPUs with the external connectors available. So we have, for instance, sold one of those to a company that does ship simulators, where you have a physical ship bridge that you walk into, and there are projectors all around in the room, and giving a 360-degree view of the surrounding area. Very cool stuff. And they use one of those machines, and it's quite good because the previous generation of the same simulator had to use 22 individual servers. So they were quite happy about that upgrade. The thing about rack servers is that you need to be aware of. The GPUs are made for passive cooling. There are no rooms for fan in this sort of tight environment. So the cooling solution are just metal, and the fans are all placed in the chassis. So you can see there is a rack of row of fans here, and there's also some fans pushing over here. And that means that not all GPUs are suitable for putting inside a rack. For instance, the commonly used workstation GPUs, the GeForce line, cannot be used in a rack server because they have top-mounted power connectors. There are no room for those, and you have a fan which actually blows blocks the airflow when you have fans in the chassis instead. This is actually a better place to show the top-mounted power. A GeForce will have their power connectors here, which will actually hit the roof of the chassis, while a Quadro and a Tesla has the power connectors at the end, which allows them to be fitted tighter together. Yeah, that's the first type of servers. Blade solutions, that's a more densely packed setup. You can have more GPUs in a tighter space than in a normal 4U, but you still get the advantage of having fully redundant setup with a shared redundant power, and you can hot swap each blade individually. So basically it gives you the flexibility of a setup of single servers, but at a reduced cost. So if you need a lot of servers, this is the way to do it to get the cost down. But just as the normal rack servers, only for passively cooled GPUs. And the final type of server or workstation is the tower. And that's what many of you are used to, because then you can fit normal GPUs, the workstation gaming GPUs, if you like, the GeForce series. They have room for the top-mounted power. But as a NVIDIA Tesla partner, I have to give you a word of caution. A gaming GPU, the GeForce, is not constructed for 24/7 use. It is much cheaper, but it's basically not designed to be used all the time for 4 to 5 years. A GeForce also does not have ECC memory, so it's not as good at doing double precision calculations. And some programs limit the amount of features available if you try to use a GeForce compared to a Quadro or a Tesla. And there can also be differences in the support you get from the software vendor. That being said, a GeForce is often a very cost-efficient way to get started with using GPUs to see if they actually improve your daily work. And if they do, you can go on and then buy a rack system or a dedicated render box later on. Okay, tips for GPU solution design. The most important thing, check out if your software actually supports it. Trial versions are great, and as I mentioned, using a GeForce card to test it, to see if it's actually feasible. Will this give you a boost in the performance? That can be a very good proof of concept, a way to get your boss to approve the funding needed to get a dedicated render box. The second point to worry about is the power. A fully spec GPU server will require a lot of power, because each card can take as much as 250 watts. So if you have 4 of them and a couple of powerful CPUs and some hard drives and so on, you can end up coming close to 2,000 watts per U, which is a lot. But for that power, you get you couldn't get that amount of compute power in any other way. So it's very efficient power-wise as well, but it still is a lot of power. And some server rooms have limitations, and how much cooling capacity you have, how much UPS capacity you have, etc. So that's something to worry about, or certainly to check out. And the third and fourth issue is, are there any other bottlenecks popping up? And the first one to worry about are storage. And there are 2 easy ways to get around that. SSDs, or even more performance boosting, NVMe. NVMe is basically a flash-based storage, just as an SSD, but instead of being connected to a standard SATA or a SAS controller, it's directly attached to the PCIe bus on the system. And a PCIe attached storage has almost 5 times the bandwidth of a SATA attached SSD. And this is not something that is theoretical. You actually get that performance. So if you have a good enterprise grade SSD, you can get around 500, 550 megabytes a second of read-write performance. NVMe device, you can get 2,200. It's very, very fast. And 80,000 IOPS. Yeah. And it's the good thing about NVMe compared to earlier versions of PCIe-based storage, just such as Fusion IO you may have heard of, or other dead sort of third-party PCIe disks, is that NVMe is a standard. So NVMe is being delivered by Intel and by Samsung and all the other major flash manufacturers. And that means that the price is actually quite good. And 400 gigabyte NVMe drive is about 30 to 35% more expensive than a 400 gigabyte SSD, but at 4 times the performance, at least. So it's very, very cool. And the final point, the last bottleneck to worry about, is the network. And thankfully there are good options there as well. 10 gigabyte LAN has now become quite cheap, especially if you buy a system with 10 gig integrated on the motherboard. You can get then 10 gig ports as low as maybe 1,000 kroner. The switches are also coming down in price. And if 10 gigabyte is not enough, then there are faster options. InfiniBand is a preferred method of communication in high-performance computing environments. You can get that in 56 gigabit or even 100 gigabit. But at those speeds, the cost of the switch is significant. So I wouldn't go directly to those if you don't really know that you need it straight away. But if you buy a system that has at least one PCIe slot available, then you can always put an InfiniBand card in later and get that performance if needed. So it's not like you have to you don't have to jump on that wagon straight away. Okay. My final slide. Compute powers of GPU can dramatically cut down the time it takes to render if the software supports it. That's the most important thing I want you to remember from this little presentation. There are many programs that support GPU acceleration today, and many more are on the way. And as a hardware vendor, we are happy, of course, to give you quotes and talk about the solutions that can actually support this for you right now. Please come by in one of the breaks and we can have a talk if there's anything you wonder about. Thanks very much for the attention, and this presentation, of course, is available for any of you that want it. So I assume it will be sent out after the event. Yes. Thank you very much. And hopefully there's coffee now.